This lab is based off the observations of Felix Baumgartner and his 120,000-foot free fall from the Earth's atmosphere. Two of the central questions guiding our observations are whether it is possible to break the sound barrier of 340 meters per second through freefall, and how high would one have to jump from to achieve this feat. Our prediction is that using given variables such as the man's mass, which is 100 kilograms, and the drag constant of a man in freefall, we should be able to calculate the terminal velocity of the man. The equations central to these calculations are Newton's second law, final velocity equals initial velocity plus F net over mass times the change in time, and the drag force equation. Drag force equals 1/2 drag constant times velocity squared. Using these equations, we can solve terminal velocity by setting drag force equal to gravitational. We can then isolate velocity and find that it is equal to 55 meters per second. Here is the model of the freefall, and as you can see by the graph, the velocity or slope of the curve starts to become constant. The code to create the model just involves putting our force equations into a while loop that will constantly update each force. As we calculated earlier, the terminal velocity was 55 meters per second, nowhere near the speed of sound. So how did Felix accomplish this seemingly impossible feat? The answer is that he was dropped from a distance so high in the atmosphere, the air would be too thin to stop his acceleration. With such thin air, drag force was negligible. In our next model, we assume zero drag force, and we see that the acceleration never stops. This means that the speed of sound and beyond can finally be achieved, assuming Felix is dropped from high enough. The code used to create this model is the same as before, except drag force is omitted.